radical A minus B. In this case, one's radical, one's not. But if there's any radicals involved, what happens to the radicals when you finish up with this? Yeah, because everything is squared. Conjugates multiply to make a difference of squares, and squares kill radicals. Okay? So remember, we used this method to kill denominators when we were rationalizing denominators in 11.5. We wanted to kill rationalizing denominator means no radicals in the denominator. If we wanted to kill a radical, we multiply it times itself. And the very nature of conjugates, which gives us a difference of squares, means we have a square minus a square. So if there are any radicals, that means that one of our terms, one or both of our terms, is going to be a radical squared, which means no more radical. Okay? So if you want to kill a radical, multiply it times itself. If you want to kill a radical binomial, you multiply it times its conjugate. Okay? So this goes straight to our first term, squared, minus, because O and I cancel out, our minus, mixed signs, our last term, squared. Okay? And because this is a radical squared, this becomes A. And this is just not a radical, so it's just B squared, whatever that number is. Okay? But still, there's no more radical. Okay? Radical's gone. Okay? Now with complex conjugates, it's the same idea. Complex conjugates would be, rather than binomials with or without radicals, it's complex numbers, but they will behave with the same pattern. A plus bi times A minus bi. Two complex numbers with the same A's and the same bi's, but one's plus and one's minus. Okay. Well, if you FOIL this out, then you're going to have, for your O and your I, will be negative ABI and positive ABI, which are going to cancel out. That's the nature of conjugates. So if you have complex conjugates, you recognize it. If you want full credit, you recognize it, and you go straight to the expanded version, which is your first, which is, hey, complex conjugates, I'm going to have a difference of squares. So your first term, put it in parentheses, square it, minus, because it's a difference of squares, difference, minus. Your second term now, instead of just being a plain B or even a radical B, is a BI. Put the entire thing in parentheses and square it. Still a difference of squares. First term squared minus the second term squared. Same pattern. Now, if radicals are involved, then the nature of radicals is that squaring a radical just releases the radicand. Okay? So, same pattern, but you have to understand how radicals behave. Here, same pattern, but you have to understand how i's behave. Because when you simplify this, this is your real number component, so it's just going to be a squared, whatever that number is, minus, and that square belongs to both the b and the I, so you end up with b squared I squared. What happens to that I? Right, that I squared cancels out and throws the negative out front, which changes a minus to a plus, and you end up with a squared plus b squared. So complex conjugates you can write in one of two ways. You can expand it either way. I generally encourage students to do this way, and it's the way I'm going to show with the examples because it's consistent with the same patterns before. If you see complex conjugates, A minus BI, then immediately put your A in parentheses, square it, minus your BI in parentheses. The entire first term and the entire second term with a minus sign, both of them squared. Okay? But notice how there's no more I here. Notice how multiplying by a complex conjugate, just like multiplying by an I kills the I, multiplying by a complex conjugate, there's no more I. This is just a number and a number. You'll be able to simplify this to a single number. Okay? A and B are real numbers. There's no more I. So another way to think of complex conjugates is A plus BI times A minus BI. You can go, because you know how the I squared is going to behave, you can go straight to the first real number squared plus the second real number squared. Because you know that I squared is going to flip the sign. But if this confuses you at all, because the big difference here is this still involves an I that will be squared and flip the sign, whereas this, if you write the plus sign, don't write the I. So if that's confusing you, it's like if you're writing a plus sign but also writing the I, that's bad. Okay, it's either one, which will flip the sign, or the other. No I, it's already gone, so the sign is already flipped. One or the other. So if you're getting that confused or mixed up, then I recommend sticking with this one. This is how I'm going to show the examples, just to be consistent with everything else we've done. But as you do it, you're going to start to notice that. Okay, you got to pay attention to those patterns and see what's going to happen. So, complex conjugates, here's a couple of examples. Do 7 plus 3i times 7 minus 3i. And let's also do one with radicals. Square root of 3 minus 5i. Here's a complex number where our pure real number is a radical. That's fine, it's still a real number. You might also have one where you've got a radical as your b. So square root of 3 plus 5i. So for that matter, I'll do 2 plus I radical 6, 2 minus I radical 6. Either way, it's our first term squared minus our second term squared. Like I said, I'm going to do the full just to be consistent with the a squared minus b squared. First term squared minus the second term squared. Remember that square belongs to the 3 and the I. Comes negative 1. And you can see the I is gone. You're left with a real number. Complex conjugates will leave you with a real number, which you can write as 58 plus 0i if you're required to, but the whole point is you get just a real number. You just get a plain old real number, which is what's going to help us with our next step. So it involved a radical, so of course a radical squared is just the radicand. And here the 5i squared, the square belongs to the 5 and the I. This square belonged to the I to make it I squared. It also belonged to the square root of 6, which just released the 6. So if I clean this up a bit, it's 4 minus 6i squared. And of course, then that I squared makes that plus. First term is 1, second term is I. 1 squared minus I squared. So that's minus, and that I squared is negative 1. Gotta be real careful here. If you got nothing else, you're not just flipping a sign. Because it doesn't just disappear. There's already a minus sign there, and I squared itself is negative 1. So what is our answer? 2. Yeah, not 0. This wasn't 1 minus 1. It was 1 minus negative 1. Now, just to finish up, and it's a little rush, but just so you can touch on these things, you'll be able to tackle them on homework. It's the same idea. The last step here is dividing complex numbers, but dividing complex numbers uses this skill we were just looking at. So it's a way to practice this a little bit more. So, to divide complex numbers, because we look at adding, subtracting, and multiplying, including our special products. So divide complex numbers. To divide complex numbers looks a little strange, because we think, oh, division, but basically what we're trying to do here is we're trying to kill the I in the denominator. So we're given the division problem as a quotient, and a quotient has a numerator and a denominator, and our job to divide complex numbers is basically to kill the I that's in the denominator. Okay? So this is much like, rationalizing the denominator. This was the same skill we did in chapter 11, rationalize the denominator 11.5. We couldn't have a radical in the denominator, so how do we get rid of a radical? Multiply it times a radical. Or if it was a radical binomial, we multiplied it times its conjugate. Multiplying a radical times itself kills the radical. Multiplying a radical binomial times its conjugate kills the radical.
So would you
Same thing with i's.
Like, would you try to square it? Like square it
Exactly. Yes.
Square the top?
So two quick examples, 7 over 3i. We have a single term, or do we have this is a division problem, 7 divided by 3i, but basically dividing complex numbers means we're going to kill the i. So, is this a single term as pure imaginary, or an imaginary complex binomial, complex number?
Is it complex?
Okay. Well, everything's complex, but is it a full a plus bi complex?
No.
No, it's just an imaginary term. So to kill the I, we just have to multiply times I. Okay? Now, do we have to multiply times 3i?
No.
No. We could, if we're fair to the top, but why make your life more difficult with bigger numbers? To get rid of that I, which is all we're trying to do when we divide, we just have to multiply times I. And whatever we do on the bottom, do on top. That's like multiplying times 1, didn't change the value. Okay? So this gives us on top and on bottom. What happens to that I squared? Yeah. So basically, if this were negative, we'd make it positive. It was positive, so we make it negative. The I squared cancels out on the bottom, becomes 3 times negative 1. Well, that's negative 3. We can just throw the negative out front. So this division problem is completed with negative 7i over 3. This can also be written as negative 7/3 I. In fact, if you were asked to write it in complex number form, you should write it as 0 minus 7/3 I. Okay, I got 2 minutes left. Let me show you that one last example. We're right on time. This is just multiply. If it's just a single pure imaginary, multiply I over I. And then you're going to simplify using, understand what I squared means on the bottom, which leaves you with the plain old 3. If you end up with a fraction, reduce it if you can. Pull it out in front like a fraction coefficient of I. And if you're asked to, write it in complex number form. All right, so here's where it gets a little weirder looking, okay, but this is going to help us with the rest of our skills too. You're going to see this come up again. Now this isn't just this is 3i, this is a full complex. This is a plus bi.
So you would multiply the I times everything at the bottom?
You would multiply. What kills a full complex number? Its conjugate. Yeah, because remember, every time we multiply conjugates, we end up with just a number, just a real number. No more I. Okay? Because it was a square minus a square. No more i's. Okay? So if we want to kill just an I, imaginary unit, we multiply times I, we get our I squared. Gone. If we want to kill a full complex number, we will lock it up and we'll multiply it times its conjugate. 3 minus I. Okay? If this were 3 minus I, we'd multiply times 3 plus I. Okay, just like our radical conjugates that we did in the last unit. Now be fair on top. Okay, now simplifying is a little different than the last unit. Okay, so first we'll write this as 4 times 3 minus I on top. And on the bottom, this is complex conjugates. We have 3 squared minus I squared. Okay. Now be careful because this is 9 minus.
That'll equal positive.
Yeah, 9 minus negative 1, which means 9 plus 1, so that becomes positive 10. So be real careful when you're simplifying these. You keep track of your negatives. So this was 9, 3 squared, minus negative 1. So this becomes, and unlike in the last chapter where I said leave it factored, because you may just have to cancel out, you may have to just reduce. That was true for the last chapter. For this one, you need to distribute. Because we're going to have to write it in a plus bi form. And we can't do that if we have any parentheses. Last chapter didn't matter. Keep the parentheses, keep it factored. reduce outside things to lowest terms, move on. Here, we've got to change it to this form, so we have to kill any parentheses. So, distribute this to get 12 minus 4i. And on the bottom, 9 minus negative 1. Okay. Now, to simplify that further into this form, we have to break it up into two things, something plus something, instead of just one radical bar. And so I point you towards your rules for basic fraction addition, which is if you have, let's say, a over c plus b over c, right? Fractions, adding fractions with common denominators. Well, that equals, you combine your numerators over your common denominator, right? Well, you know what? This goes in both directions. If you have something added or subtracted in your numerator and it's over a common denominator, you can split it up to the first thing over the common denominator plus the second thing over the common denominator. That's a fair move. That denominator belongs to each separate thing that's on top. Okay? So that's exactly what we have here. We have an a and we have a bi over common denominator. Well, we're going to give that denominator to the a and we're also going to give it to the bi. So this equals 12. Basically, the one other way I sort of refer to this is a two-headed fraction. Okay? Well, we're going to separate those twins. So we got 12 over 10 minus 4i over 10. Okay? That's a fair move. That's this rule right here. Now, simplify each one completely. 12 over 10 becomes 6 over 5. And 4i over 10 becomes?
2i over 5.
Right. But let's go ahead and also write it as a fraction coefficient. So 4 over 10 is 2 over 5. Pull it out as a fraction, and the I will be written right at the bar. And that's in your complex number form. Okay? So the principle, like with radicals, is the same. Complex conjugates to kill the I in the bottom. The simplification is just a little different because this is your aim right here. So distribute to kill parentheses, share the denominator, reduce to lowest terms. Okay. I'll be down in the lab in about 5-10 minutes. And see you on Thursday.
See you Thursday.
Okay.